Hi guys, I hope you are having a very great weekend and today we are starting off with a very interesting topic which is level order traversal. So today the latency is even less and I should be able to see your chats even quickly. So I have done some changes and I hope I'll be able to answer your questions even quickly. Hi Sampath, hi Samir, thank you so much for showing up. So the question that we are actually doing today is very important not only for trees, for graphs and not only for binary trees, but it is the same concept that is going to be used literally everywhere. So I cannot emphasize enough on how important this particular concept is. So, just stay with me and try to understand it. I'm going to break it down in a very easy way. Okay. I hope you are with me. Can you just quickly confirm that you're able to hear me, see me properly, that you are able to see when I write hello over here? Right. So once you confirm that, let's quickly get started with the question that we are going to be doing today. So we are talking about, okay, awesome. Thank you, Shivai, for confirming. Hi, Sampath. Thank you. Okay, great. So what we are going to be doing today is we are going to be talking about level order traversal. So in level order traversal, what we do is, can you also see the screen? I wrote hello. You can see that, right? I just want to quickly confirm that you are able to see the hello that I've written. Can you? Yeah. Okay, great. Okay, so what we'll be doing today is we'll be talking about level order traversal. Now, what does level order traversal mean? Let's take a binary tree. Okay, so this is a binary tree, two nodes at each level. Okay, now when I say level, what do I actually mean? So this is one level, this is another level, and this is another level, right? So what do we mean when we say level order traversal? So when we say level order traversal, it actually means, so if my nodes are numbered like this, 1, 2, 3, 4, 5, 6, 7. We are going to traverse our tree level by level. So this is level 1, this is level 2, this is level 3. So the traversal of this particular binary tree will be 1, 2, 3, 4, 5, 6, 7. So basically we are going to go like level 1, level 2, level 3 like that. So we are going to go level by level. Okay. Now, what is the difficulty over here? Why is it such a big deal that we have to go level by level? The thing is that here for each node, we have like a left child and a right child. So for each node, we can go like this only, right? Left, right, left, right. But after this node, I need to access this node. Now, how do I do that? That is the main problem with level order traversal, right? Like when I'm at 4, how do I go at 5? Because this is the parent. Now I can go from parent to child, but I don't know how to go back to parent or how to go to 5, right? So my problem over here is that once I'm at 4, how do I go to the same level? How do I traverse, right? That is the issue over here. Are you able to understand the problem that is when we are talking about this? Can you quickly confirm? I am restarting the screen sharing. 1 second. So there was some problem. 1 second. So the problem over here is that we have to see that how do we traverse level wise. Like if we have one node over here and we cannot actually access the parent of that. So how do I go towards the same level, right? So that is the problem. I need you to think about it at, what would be one possible way so that I can go level wise. So can you let me know in the comments what are the things that you can think of when I say that okay we have to traverse level wise. So I am saying that, let me show you again. So I am saying that if you are at 4 over here, you have to go to 5 now. As simple as that. This is the main problem. How will you go from 4 to 5? Now, how will you go from 5 to 6? How will you go from 6 to 7? So this is the problem, right? Yes. So Shailesh has answered using BFS. So when we say level order traversal, we will actually be doing BFS. Now, what is BFS? We'll be discussing that. The concept that we are going to understand today, we are going to be using that in graphs as well in all sorts of trees. So this is an extremely important concept. BFS is something that will be asked a lot in the interview. So you need to know this properly. Okay. So what actually happens over here is this is called breadth first search. Why am I calling it breadth first search? Because we are going breadth wise. So like this is one breadth, then second, then third. So we are going horizontally, right? We are going level wise. So level order traversal or breadth first search. Now, Shailesh had answered using BFS, but Samir had answered using Q. Are both of them wrong? Let's talk about, what Samir is saying. Why do we need to use Q over here? So we should be able to understand that why we are using a particular data structure in a particular place. Okay. So let's try to understand that why Qs are important over here. So now let's get back to our diagram initially. What was our problem? Our problem was that I am over here. How do I go back over here? Now, what is the common thing between these two children? That this is the parent, right? Now, suppose in one place, I knew that what was the right child of the parent. I am at left. If I knew what was my right child of the parent, I would have gone there, right? Now, let us see again. So here, this is my first uh, node that I come across, right? So this is my first node. After this first node, who are the first node's children? It is 2 and 3. So I keep my 2 and 3. Now I was at 1. I know the children of 2 and 3. So who are the children of 2? Children of 2 are 4 and 5. Now I am just writing them. Okay. So I have added the children of 2. Now, who are the children of 3? It is what? 6 and 7. I'm going to add like this. Now, suppose after that, now we have considered children of 3 also. Now, suppose 4 also had children. Suppose 8 and 9. I should have added 8 and 9. So, you basically see that as I am going through the elements, I am dealing with their own children. Like 1, there its children. Then 2, then 2 ka children, 4, 5. Then 3, 3 ka children, 6, 7. Right? So in the same order in which I am coming across the elements, I am going through their children also. Is this point clear? That whatever node I found first, I need the children of that node first. You have understood this much? See, whichever node at we are at, we need that node's children first. Okay? Uh, thank you, Shiva. Thank you, Simran Samli. Thank you for appreciating my work. Really means a lot. Okay. Now, we need to find a data structure such that when we come across a particular node, we come across its children first. So in the order in which we come across nodes, we want the nodes in the same order. Now, which data structure does that? First in, first out. The node that we came first, we want that out first. Why am I saying that again? Just think about it. See, when I had one first, I needed his children first, which was 2 and 3. Then I had 2, I needed 2 ka children, which was 4 and 5. Then I had 3, 3 ka children. So whichever node was pushed in first, I need that node out first, right? So first in, first out. It's okay if it's not clear. Let's take more example and let's understand. So till now, what all we have discussed? We have discussed that, okay, firstly, our main problem is that we have to go to the right of the same parent. How do we do that? Okay. Now for that, what did we see? We saw that, okay, we can do that by, going through the parent ka children one by one. In the same order that we are going through the nodes, we need their children in the same order. Now we need to think of a structure that, does this. So we need a structure that does first in, first out. So that is the structure that we are using Q. Okay. Now we are actually going to make the diagram and understand that how Q is being used over here. And then we will try to convert it into Q. Okay. Understood? Sorry, this is getting disconnected again and again, but don't worry about it. Okay. So now what am I going to do is I'm going to dry run for you. So again, this is the tree that we had 2, 3, 4, 5, 6, 7. Guys, if you have any doubt, this basic is very, very important. Again, it is going to be used in graphs everywhere. It is going to be asked so much. This is like the basic that you should know if you are into data structures and algos. Okay. So we start from our root. We had a root. We started from there. Okay. We have taken a Q. What does Q does? It does FIFO. First in, first out. So whichever element I'm going to push first, I'm going to take out first. So I push in first. Okay, I've pushed in first. Okay. Now what am I going to do? I'm going to push first ka children. So first ka children are what? 2 and 3 in the same order. So 2 I'm going to push first, then I'm going to push 3. Okay. So 2 and 3 I've pushed. Now since I'm done with all the children of 1, what am I going to do? I'm going to pop it out. So what is Q does? It does FIFO, first in, first out. So this was first in, so it is going to be first out. As soon as I take it out, I am going to do what? I am going to print it. First I have. Now, what is the next element that I have? I have 2. Now, 2 ka children are what? 4 and 5. I am going to push it to the queue. 4 and 5. Okay. Now, I am done with all the children of 2. What am I going to do? I am going to pop it out. I am going to print it. What is the next element that I have? It is 3. Who are the children of 3? It is 6 and 7. I am going to put 6 and 7 over here. Now what do? I am done with all the children of 3. I am going to pop it out and print it. Next, 4. There are no children of 4. If there were children of 4, I would have pushed it. But since there are no children, we are done with all the children. I'm going to pop it out. Right? So what am I going to do? I'm going to pop it out. Similarly, 5, no children, I'm going to pop it out. 6, no children, pop it out. 7, no children, pop it out. So did you see that how we were able to go row wise? Because we had all the children together, right? That is why we were able to go level wise or breadth wise. So this is why breadth first search or level order reversal. Understood this means, guys, because we are going to convert this into code. Okay. Why have we taken a queue over here? Because we need FIFO, first in, first out. The elements that go in first, we need to take them out first because we have their children. Now we are done with it, we can take them out. The next element, we put their children, we can take them out. Okay, understood? Great. Can one of you quickly confirm in the comments that you were able to understand this one before we move ahead with the code? Yeah, okay. Thank you so much, Alice, for that. Okay, now what we are going to do is we are going to move ahead to our code. Okay, so this is the question that we'll be doing today. This is level order traversal. So we are given a binary tree. We have to find its level order traversal. Level order traversal of a tree is breadth first travel of the tree. Okay, are you able to see the code? Are you able to see the question that we are dealing with? Are you able to see everything? Then we'll go ahead. So this is the tree. What will be the level order traversal? So this is the first level. So 1. What is the next level? It is 3 and 2. So 1, 3 and 2 will be the output. Similarly over here, this is the tree. First level there is 10. Second level is 20 and 30. Third level is what? 40 and 60. So 10, 20, 30, 40, 60. Okay. Done. Great. Let's start with the code now. Now let me just quickly move this. So in node there is data left and right. Okay. So I'm just going to and expand this so that you can see the code properly. Okay, great. So we have to start writing the code over here. We are given only the root node. Okay, so we have to return the answer in a vector. Basically, we are going to store all the elements in a vector. So I'm going to call it what resulted. We have to store over here. We know that we need to use a queue. Now the question that comes, queue of integers or queue of node? What should it be? Now, we have to think of these small things. Now there are data. Can we just store the queue of integers instead of the nodes themselves? So we have to think about this. That is not the case. We can't just store integers. And I want you to tell me why we can't just store queue of integers and why node. Samir, very good node, but why node and why not integers? You have to tell me. I will tell you when we come across the problem. Okay. Right now I'm storing queue of nodes. I'm just calling it queue. Okay. Now what do? I first push my node value that I have. So I had my root value, I pushed that. Now what am I going to do? I'm going to keep traversing the queue until it is empty. So this is my condition that I'm going to, don't worry if it is not clear, it is going to be clear. We are going to do this till the queue is not empty. So Samir is saying we have to find out children of node. Very good, Samir. So because when we come across every element in the queue, what do we have to do? We have to check the children of the nodes. If we have just integer, we cannot access the children. We have to get the children of every particular element in the queue. That is why it is a queue of nodes and not queue of integers. Shiva has also answered because we have to visit every node's child. So we require the entire node information. Very good, Shiva. Very good, Samir. Now what we are going to do, I'm going to keep traversing till our queue is empty. Basically, we have no more nodes to travel to. Okay, so now what am I going to do? I'm going to pop the first element. The first element that I have, that the first and first out. So there's at least one element that I know. I've already pushed my node, right? So what am I going to call? I'm just going to call it F right now, basically the frontmost element, just keeping it very simple so that you can understand. So I'm going to call it what? I'm going to call it Q ka front. Okay, so this is how my front node looks. Okay, now what am I going to do is my front cup, I need, so I need the children of those, right? So if my F has a left child, I'm going to put it to the queue, right? So q dot push, oh sorry, q dot front. Okay. So I'm going to do q dot push and I'm going to push what? I'm going to push the left child. Okay, now I have pushed the left child. What am I going to do? I'm going to quickly check if there's a right child of the front element. If there's a right child of the front element, I'm going to do what? I'm going to push it. You remember in the diagram, what were we doing? We were checking if there's a left child, we'll push it. If there's a right child, we'll push it. Right? We have done this much. Once we have done this much, we know that this is also part of the answer. We have popped it out. Okay, I access the frontmost element. I also have to pop it out, right? So after popping it, how can I do that? I can just do q dot pop. Now I could have actually popped it up also. So instead of doing this here, what I could do is actually I could pop it here only because I have saved the element in over here. It doesn't matter where I pop it. I'm just popping it earlier to save some space. So now what do I do? After I've popped it, I need to store it in the RES also. So I'm going to push back. So in this, I'm going to store FK data. Okay. So this I'm going to keep doing until my queue is empty. So at least until there's even one element left. See, if there is no left and there's no right, we are not going to go back to it. Then the queue will become empty, right? It's very simple stuff. When there's only one element, what is going to happen? We have pushed one element. We will come into this. There's no left child, there's no right child. We will just push that element and we'll get out. So think about the cases when there is only one child, when there are two children and there are three children, how it is going to work. Okay. I'm going to be returning RES from here. Let's compile and see whether this works or not. Guys, if you have any doubt, if you have any question, please feel free to ask me. Okay, I'm here to clear your doubts. It compiles. Now let's submit and see. Also, what will be the time and the space complexity? Let's start thinking about it. So we have passed all the test cases. It worked. Now let's look at this expected time and the space complexity. It is order of n. And what is n? N is the number of nodes. Now see, how big our queue can be. At a particular time, we would have pushed all the elements of the queue. So how big our queue can be? It is order of n. N is the number of nodes. So what is the space complexity that we are using? Order of n. What is the time complexity? In the worst case, we are going through all the elements once, right? So we are visiting all the elements only once. So the time complexity is also order of n. So the time complexity is order of n, space complexity is order of n. Congratulations, you have just understood a very, very important concept, which is spread first search or which is uh, level order traversal. There are so many questions related to this, and I want us to practice a few more in the next few days. We'll be doing level order traversal in graphs, we'll be doing level order traversal in more trees, and we will see variations of this question. I was asked this not only in Intuit, I was asked this in a lot of my placement interviews as well. I have asked this so many times. I cannot emphasize enough on how important this question is. I hope you understood it, and I hope you will show up tomorrow. It's a weekday, so we are going to meet at around 5 or 6 p.m. or maybe 9 p.m. What works better for you, let me know. Okay, see you tomorrow. Bye. Have a great weekend.